Hello and welcome to today's webinar on a very exciting topic, which is about low noise amplifier design. In this webinar, we will take you through concept to fabrication. Here is a quick agenda for this webinar, and we will go and talk about each of these topics in a little bit of details so that you get a fair idea what it takes to produce a very accurate and highly effective low noise amplifier design. So beginning with LNA theory and fundamentals to set the basic stage, we will then walk through each of these steps to perform a good low noise amplifier design. Now before we start, subscribe to my YouTube channel if you haven't done so already. On this YouTube channel, you will find multiple videos about software basics and how to do different things in the software, as well as plenty of practical design tutorials. So hopefully you will find it very valuable in your learning journey and also become more equipped RF and microwave circuit designer. Alright, so let's take a quick look at LNA theory and fundamentals and then begin our exciting journey about the designing of LNA. Now most of you already understand what is a low noise amplifier, and it's a pretty important piece, especially in the receiver subsystems. Now this special category of amplifier is designed such that it boosts your signal to noise ratio at the output. What it means is the signal gets amplified, but noise gets amplified by a very small amount, and that is called noise figure of low noise amplifier. So designers, while designing this special class of amplifier, can minimize additional noise by choosing low noise component, selecting proper operating point, and making sure they select the right circuit topologies. Now minimizing additional noise must also be balanced with your other design goals such as power gain and impedance matching. What does it mean? You will understand as we walk through in today's webinar, and you really understand where this power gain and impedance matching considerations comes about. So LNA is a key component in the front end of the radio receiver, which helps you to reduce unwanted noise. In particular, in most receiver, the overall noise figure is dominated by the first few stages, as you understand. Now, by placing LNA close to the signal source, that means around antenna, the noise from the subsequent stages of the receiver chain can be reduced because of the gain created by LNA. That is why LNA has two important metrics which a designer needs to contend with. One is the noise figure, which is the metric to control how much noise additionally gets added in the signal, as well as the gain. Higher the gain of your LNA, overall noise figure of the receiver can be controlled. So if you look at the Friis equation, which gives you a pretty good idea about cascaded noise figure, as you can see, the initial few stages contribute the most in the overall noise figure of a receiver. So by controlling the initial few stages, you can control the overall noise figure, which goes a long way in your receiver working more effectively. So here is a simple calculation given for your understanding, which you will find also in many of the theory books. Now for this tutorial, we will take these specifications to design our LNA so that you can understand each of the steps and how critical is each step during the design process to achieve these design objectives. Now when it comes to choosing right technology, primarily you have three choices to design RF low noise amplifier. If you're an IC designer, you can go ahead and select MMIC process. Typically a gallium arsenide p-HEMT process is a very popular one, or you can choose to design your LNA on a PCB or RF board, as well as you can decide to design your LNA using silicon or CMOS topology. Now each of these techniques have different pros and cons, which I have listed here. Any of these IC selection is a good choice if you have to produce the circuits in a bulk quantity, because that's how you recover the IC fabrication cost. But if you are producing in a mass quantity, then per piece cost becomes very, very affordable. Where if you have to design 1 or 2 or 3 kind of circuits, then IC can become prohibitively expensive. So PCB or RF board is a decent choice to consider. The only disadvantage in PCB obviously is you are going to have much bigger size of the circuit, but then the cost would be nicely controlled since you are not looking to buy in a bulk quantity, or you want to produce in a bulk quantity. So in this webinar we will focus on RF board since it is like every man's tool. However, the concept you are going to learn is equally applicable whether you are doing MMIC or RFIC kind of designs. Now, if you are doing a PCB design, you have to first find a low noise device which you can use in order to design your LNA. It could be a BJT, or it could be a HEMT or a FET component. A good thumb rule to remember is to pick a device whose noise figure minimum, or the minimum noise figure, is less than or equal to the half of your overall noise figure which you are looking at. And the lower noise figure minimum is, better chance you have for success in meeting the design specification at the end. Now, another important aspect to look while selecting any particular device to design your amplifier is your gain. As we just discussed, in the cascaded noise equation, gain of the amplifier helps you to reduce the overall noise figure of the receiver. So selecting good enough gain and maintaining good overall noise figure is the key to meet the overall receiver system level performance matrix. So based on my specifications, since I am looking to target around 1.4 dB of noise figure and better than 14 dB kind of gain, if I look at this particular device, that seems okay, and this is what I will use in my design work. Now, another approach is when you get to design, once you finalize the device, you need to find out what kind of model is available for that particular device. If you have a nonlinear model, that's appropriate, because then you can perform linear as well as nonlinear analysis for your amplifiers. Although LNA is largely, most of the specifications are linear, but still you have a couple of specifications like P1dB, output IP3, which are nonlinear specification. So by having nonlinear model, you can perform all kind of simulations and ADS. But in many cases, you might have a device where vendor is unable to provide you with a nonlinear model, and the best they can do is to provide you a 2-port S parameter file, but that file is with noise data, which is the critical information if you have to simulate noise figure of the low noise amplifier which you are designing. So either of these approaches will work. The only downside when you use the S2P file is you cannot perform nonlinear simulation. That means you cannot characterize P1dB or IP3 of the amplifier which you are designing. But that's not a major hurdle, because usually low noise amplifiers operate at a very low input power level, so there will not be many occasions where your LNA will reach the output P1dB point, so there's not a major concern. So either one of them you have is equally good enough. And all the design steps which we are going to talk about in this webinar is equally applicable no matter whether you are using a nonlinear model or whether you have a S2P file, except DCIV curve simulation, which you cannot perform if you have a S2P file. Other than that, everything is equally valid in this webinar. Now, when it comes to impedance matching, remember earlier we discussed about the noise figure should be then balanced with impedance match and the gain. So here is why. Now, when you have read the theory about amplifier or impedance matching, we have often spoken about complex conjugate matching, because that gives you the maximum power transfer, hence appropriate. Well, when you're designing LNA, the input side of the LNA has to be matched to the optimum noise point, which often is referred as gamma optimum. Now, at this impedance, your amplifier will produce the minimum noise, and largely, in most cases, in almost all cases, this impedance will be different than your complex conjugate matching. That means when you are looking to match the input side of your amplifier, trying to achieve a best possible S11, that may not be possible. So input matching is always a compromise or a balance between the return loss and the noise performance, and that's where the most critical designer's acumen is tested, how to find the best compromising point where you can get best of both of these worlds. On output matching side, that's complex conjugate match, because then you are looking to obtain maximum possible gain out of this device. So output is always matched to complex conjugate. The input side is always a balance between the noise figure and S11, and that's the whole piece. Once you understand that piece, you can easily go ahead and design a very effective and a nice LNA. So now we can start with this fundamental, just to summarize. You decide your fabrication technology. So for now, I'm assuming, most of you may want to do board design, because this is simplest to do. You can go ahead and fabricate, you can test, you can refine your design process so that what you simulate is exactly what you measure when you measure your circuit using a vector network analyzer. That should be the goal. And anything which is not going right in between, you can refine and you can achieve that. But let me tell you from my experience, if you do things right in ADS during design phase, you will exactly get the same performance when you are measuring the circuit in your lab. So there should be hardly any different, plus minus 2% or 3% variation due to some things which we cannot control, such as manufacturing tolerance, quality of your components, and so on and so forth. So within, I would say, plus minus 2% to maximum plus minus 5%, you should be pretty much there if you do a good design of your circuit. All right, so since we are going into the demo piece, let me stop here and let me look at the chat, and I will try to answer a few questions in the chat. Let's see. Okay, so can you provide recording? That's for organizer. I'm sure you will get a recording. Can't we implement broadband impedance matching network on PCB the way you usually do on chip? What's the reason to get lower bandwidth for PCB? Okay, so the whole thing lies, it's not only impedance matching which controls the bandwidth. Many a times in order to do a very broadband, again the question is, how do you define broadband? If you do ultra broadband multi octave design or an octave design, you need to do a lot of things like using a feedback loop. You work on gain bandwidth product, all those fundamentals which you might have read in third year or fourth year of your engineering. So doing such things on PCB is possible, but then the overall size requirement, because then you might need to do 2-stage or a 3-stage design, and that will increase the PCB size to very large amount. And that's why you cannot do a lot of things on PCB that you can do in IC. In IC, if the first stage is using a feedback loop to achieve a flat gain bandwidth product or to increase the bandwidth, you can always compensate it by doing a 3-stage LNA design, because the cost or the impact is very low, because you are only dealing with few microns. So from 1 mm, your chip might get increased to 1.5 mm. That's why ICs will always give you much higher bandwidth that you can achieve from PCB. But again, its question is, how do you define broadband? Okay. But there are some clever techniques which may be possible in PCB, but of course, doing multi-octave or a octave bandwidth, it's not so easy on PCB. Please share PPT of the session. Yeah, that will be shared. Local Keysight team will be sharing the slides. I'm working on high-speed communication, wide bandwidth up to 10 gigahertz of bandwidth, trans impedance amplifier, but facing problem of impedance. Yeah, that's a very specific question. You need to connect with the local team, let them see your design, and they can offer some suggestion. So there may be some clever techniques to do that. CPW to die pad wire bonding, all those things can be characterized using 3D EM simulator inside ADS. It's not that difficult. But let me tell you, their wire bonding is going to be your bottleneck, because any bond wire is like an inductor. But we do have some clever compensation techniques to decrease the impact coming out of wire bonding. Like, for example, you can put multiple wire bonds in parallel to reduce effective inductance. You can use the launch pad of the bond wire to be having a capacitive nature so that you can increase the bandwidth. So there are some options available, so consult with the local team. Without the DC simulation with S2P file and noise data, how do we decide DC feed? That's altogether different structure. For designing DC feed and decoupling network, you are absolutely not dependent on the DC simulation. DC simulation is only to find the right IV characteristics, find the right bias point. Again, for LNA design, that's not very critical. You can just look at the data sheet, find the class A operating point, and that's what your LNA will be going to use. It's always a class A amplifier LNA. Yeah. So to design DC feed, as you will see just now, when I go to bias network design, DC analysis has no role to play there. Will a piece-spice model of LNA transistor will be useful for design? Yes, absolutely, it will be very useful. You can import piece-spice model into ADS, and piece-spice model is like a nonlinear model. It essentially is a nonlinear model, and you can import that into ADS and start designing your circuit with that. How will we verify the blocker tolerance simulation of receiver? Yeah, so that's again is a very subjective. So Soham asked this question. So Soham, that's very subjective. I would say please work with your local Keysight team. They will understand the requirement a little more carefully and suggest a solution. Depending upon how deep you want to go, you can do things in ADS very easily, or we can use a system level tool from Keysight called System View, which can do much better selectivity and sensitivity analysis and blocker analysis and so on. When I buy component from Mouser, I only have the part number. Yep. So once you have the part number, you should go to manufacturer's website, and from there you can get a S2P file. Sometime even DigiKey has S parameter files available for you to download. Otherwise, DigiKey is just a supplier. If you are buying, let's say, a Skyworks or a Corvo device or Maycom device, you will always have the part number. Go to those manufacturers' website and they will have S2P file, or contact their local, distributor. I'm beginner in LNA and PA design. Want to efficient in theory, practical aspects. Okay, that's little exhaustive question. So I will request Keysight India team to somehow copy paste some of these chats so that they can take some follow-up action. So Kirti's mail is a follow-up which you need to do. There are some content available, whether LNA design, PA design. My YouTube channel has tutorial videos covering all practical aspects. So I would say that is a good start point. And of course, you have a mini textbook. Who adds noise in LNA and to overcome? Well, who adds noise in LNA? Every component, remember, have a thermal noise, KTB. So those are, so every component, every transmission line, every material will have some kind of thermal noise, and that's what adds noise to the signal. Okay. All right. Do we calculate gamma optimum considering the gain of the amplifier? No, gamma optimum is regarding your noise impedance and which impedance offers how much of noise. Can we plot GM versus ID? Of course you can, no problem at all. You can plot GM versus ID in areas very easily. In design of matching network for MMIC, which parameter design transmission selection? I don't fully understand that question, but the impedance that you require will determine the line width and all that. But in MMIC, RFIC, usually you don't worry about it unless you're doing a very, very high frequency design like millimeter wave. All MMIC and RFIC are inductor capacitor based designs. So you do things with inductors and capacitors. You don't use transmission lines for matching in ICs unless you are doing 30 gigahertz and higher kind of design. Okay, can you provide me document or DC analysis, SIPI, and thermal? Yeah, local India team should take that action item. They can give you tons of document. Okay, then how do we get the input impedance capacitance from GPDK? Oh, of course, you can do simulations, S parameter simulation that will give you everything which you need, and that's what you are going to see in the demo section. All right, so hopefully I've covered every question, whatever I can answer so far. I will revert back to this chat, at some other breakpoint when I'm going to demo this. Okay. All right, so how we are doing on time? So we have almost spent half of our scheduled time in covering the theory and answering the question. So we can then go to the live demo showing you each of these key points there. Again, the workspace, the ADS workspace I'm going to use this demo is also shareable. The local Keysight team should be able to share the ADS workspace for you to see, simulate, try out, and use it as a reference to any of the designs you might be doing. But of course, the design you are going to get from Keysight people, remember, this is not state-of-the-art LNA layout. It is not highly compact. There are a lot of areas of improvement in the layout shown because the objective was to show a flow, not to create a state-of-the-art LNA in a very compact size and all that. But once you do this baseline design, you can, of course, optimize as much as you can to reduce the size of the PCB required. Okay, let me take a couple of more questions here. Can we do impedance matching using inductor and capacitor for frequency up to 4 gigahertz? That might be challenging because capacitors, no problem. You will find capacitors easily going to that frequency. You will have problems with inductors. So I would say at 4 gigahertz, you can directly do a full distributed matching based design, or you can even do hybrid design where inductors are implemented using transmission line and capacitors are picked up from SMT vendors like Coilcraft, Murata, or such vendors. I'm designing LNA at 140 gigahertz. My circuit is single-ended. It again depends on what technology you are using, whether you are doing MMIC or RFIC. You need to be a little clever on that. And if you are doing RFIC, I would say doing single-ended design is not a good approach. In silicon CMOS, you should look at doing differential design. That will be helpful. But if you are doing MMIC using gallium arsenide, that should be okay. All right. Then somebody needs to look at what's going wrong in your in your circuit. Is free version of ADS available? Those are not student. Yeah, there is a evaluation version available. Local team can you can approach local team and they can give you 30 days of eval license. Can we get manufacturing related files for RFPCB using ADS similar to softwares like Altium? Yes, absolutely. ADS has fully featured layout tool. It can generate Gerber file, DXF file, ODB++ file, any file which your fabricator needs. Once you use ADS for this kind of RF board, you don't need any other PCB design tool. Everything can be done in ADS, and we recommend you to do everything in ADS, as you will see the reason once we go to EM circuit co-simulation. All right, so let's let's go and look at the design flow again to remind you that's the target which you are looking for. All right, so at this point, let me bring my ADS window. I'm currently using ADS 2025 update 2. It's not the latest. The latest version is ADS 2026. But since I already, set up this workspace, that version, I didn't want it to change at the last moment. But if you get eval copy of ADS 2026, there's no problem. Same workspace can be opened there. Okay, so first thing, when you use ADS, assuming you have a nonlinear design kit available, the first thing you do after you create the workspace is go to design kit, manage library, and this is where you add a design kit, which is given to you by the manufacturer or which you have downloaded from their website. And you can add library definition file, add it, and then you can use it. Like in this case, you can see I'm using a ADS internal library which has the part which I referred earlier. So that part I'm going to use is an old HP part, now Avago. I don't know whether this part is right now in production or not, but from HP it came to Agilent, and Agilent sold it out to Avago. So last I know, this part was sold by Avago, ATF 21170, and the nonlinear model is available in ADS library. Okay, so once you add this library, the first step, of course, is to set up a DC analysis. So this is what we call as DC IV curve tracer. And in ADS, so let me open up a new schematic and show you. So let's say you have a blank schematic and you would like to set up a DC IV characteristic simulation for the transistor device. ADS has a lot of templates, so you can go to insert template and you have a lot of these templates available for you to use. So if you are using BJT, there is a BJT curve tracer. If you are using FET or PHEMT, you have a FET curve tracer. Once you select that template and click OK, you can see something comes with my mouse and I can place it anywhere on my schematic. So it has a basic setting which you can tweak based on your own requirement, right? And now I need to put a transistor. So since I already added the library to my workspace, if I click on this library icon, it opens this library. So here I have RF transistor. If I look at gas FET, and here I can type in the part number to filter out the part, which you can see ATF 21170. Right click and I can say place component, and now this component is available for me to place. So now I can go ahead and use this wire to make this connection. How to use ADS? If you are seeing ADS for the first time, you have never used it, please watch. There are tons of tutorials on my YouTube channel which will speed up your ADS learning journey. Okay. So once I have the device, I can set up the VDS. Again, as per datasheet, you can go and look for the DC. So in this case, it's 0 to 5 volts. You can set up the VGS. And for example, I would like to go from 0.5 or let's say 0 to 0.2 in a step of 0.2. So remember, at DC IV characteristics. You set one VGS value, then you sweep all the VDS, then you change the VGS value, then you run VDS again. So that's what DC IV characteristics. Once you set up, just go ahead and run. You will also have the display template already come up. And here you can see the IV characteristics of your transistor. And based on your requirement, you can move this marker anywhere you want. And based on where you place this marker, you can see what's the VDS value, what's the IDS value, what's the VGS value. And you can also see the DC power consumption happening at that point. So if I change it here, you can see the power consumption is low because your VDS is low. And if I place it somewhere here, you will find the power consumption is slightly more, but your IDS is low, right? So class A operating point will be somewhere here. So based on your requirement, you can set and find your bias condition which you need. Otherwise, as I said, it's not a rocket science. In LNA, you can even refer to the data sheet and figure out what's the class A operating point for this transistor. So that's the first analysis which you do, right? So once you finalize the bias condition, now the second thing you need to check whether your device is stable or not, right? Because if you are doing a nonlinear circuit design and if your device is unstable, you will never be able to make amplifier. You will always end up making an oscillator because your device is unstable, so it will oscillate. All right. So the art of amplifier design is to stabilize the device. So here you can see I have fixed my gate bias to be minus 0.4. I have fixed my drain bias to be plus 3 volts. So that's my biasing condition. At this biasing condition, I need to check the stability performance of this transistor. I have some ideal choke. You can see this is DC feed. This is like an ideal choke which will block any AC signal coming down and conflicting with DC. Similarly, in the series path, I have DC block, which is ideal, capacitors, which does not load your RF performance in any manner. So this is, imagine this being something like 1 microfarad, which has no loading effect on your RF performance. Okay. So having this bench, how do you do stability analysis? Well, the stability factor has to be computed based on your S parameter. So in ADS, you have various type of simulators, as you can see. So you have DC, AC, S parameter, harmonic balance, and so on and so forth. Even if you want to run a SPICE-like simulation, you also have transient, which is time domain simulator in ADS. So S parameter is what you need. So we can place the S parameter controller. You can see I have defined start frequency, stop frequency, and a step. And then this library palette has multiple type of stability computation. So you can either go with mu and mu prime combination, or you can go with Rowlett stability factor. Some of you who have read theory, you might have heard about K factor. So K factor is what is called Rowlett stability factor. So this is a geometrically derived stability factor, which is called mu and mu prime. And this is Rowlett stability factor or K factor. And this is a stability measure. Okay. So both of them have to be fulfilled because these are necessary and sufficient condition. If you only simulate a stability factor, that's not necessary and sufficient. This only gives you necessary condition, and stability factor should be greater than 1, and stability measure should be greater than 0. If you have those two conditions fulfilled, you can say your device is necessary and sufficient condition for stability. Similarly, mu and mu prime, it's necessary and sufficient condition. So you can pick either or, doesn't matter, both of them will give you same performance. Now, since LNAs are low power circuits, low power stability like stability factor, stability measure, mu prime is sufficient. If you are doing power amplifier design, so these are the starting points, but they do not reflect when the right condition when your device gets operated at a very high power. But since LNAs are always going to see relatively very low power, this is sufficient. So stability is much easier to view and simulate in case of LNA. In power amplifier case, it might be little more involved, but today we are not talking about power amplifier, right? Okay, so once you have it, you can see this bench, you have mu prime. Just for the explanation's sake, I also have a stability factor. So you basically just place these components here, you run the simulation, and then you get a result where you can see. So let me focus first on here. So red curve is mu, blue curve is mu prime. All right. So you can see the mu is less than 1 across the frequency, and mu prime is greater than 0 across the frequency. So it tells you two things. You have a sufficient condition for your amplifier to be stable, but you don't have necessary condition. So if mu prime is greater than 0 and mu is greater than 1, then you will have both conditions fulfilled. But right now, your device is not stable. Now, one common question asked is, should I look at the stability factor only in the band which I'm designing for, or should I look at the broad band? Well, the general recommendation in LNA design, you should stabilize the device over its complete operating point. So if I go back to my slide, if you look at this transistor is set to be operated till 6 gigahertz, yeah, 0.5 to 6 gigahertz. All right. So that means in your simulation, you should take care of stability right from 0.5 to 6 gigahertz, because it can oscillate at any frequency. It doesn't matter at what frequency you are designing the circuit for. So once you achieve stability in the entire frequency band, that's called unconditional stability. If you only stabilize the device within your band and you let it be unstable outside your band, that's called conditional stability. So if you are going with conditional stability, your design process gets very involved, because then you need to take care of source stability circle, load stability circle, and you need to ensure that in any operating condition, your source or load impedance does not fall inside that source stability circle or load stability circle. So your design becomes very constrained, and it has a possibility when your amplifier can go into oscillation as soon as you have something wrong impedance presented, or something happens. So it's a safer bet, as much as possible, increase the or achieve the stability over the wide bandwidth. And then, so this is only initial results. So at this point, S21 doesn't have any meaning as such, because you haven't matched the amplifier, you haven't stabilized the amplifier, and so on. But at least you can see your data sheet was predicting around 0.6 dB of NF minimum at the frequency at the point which you're going to operate. All right, and you are getting decent number there, and this is gamma optimum, which is S optimum. So if you, at this point, it does not matter whether you are using transistor, or I could have placed a S2P file, and connect this DC block, run S parameter simulation. I could have plotted mu and mu prime and look at the stability and then proceed for next thing. So once I know the design is not stable, before you do any other thing, we need to first stabilize the device. So how do you stabilize the device? So how do you stabilize the device? Well, anything goes into oscillation because there is something which is storing the energy and dissipating the energy. That's how oscillations are formed, right? So if device is unstable, which usually means the the input and output of this transistor have good amount of reactance, which is causing this device to become unstable. So to dampen the oscillations, what do we do? Well, we introduce something which is resistive, which is lossy in nature. So in RF microwave, that simply means you have to attach some kind of resistor somewhere in your design. See, if you are doing RFIC design to stabilize, the transistor, they typically use inductor in shunt, which they call as degeneration and degenerate. In PCB, never put anything to the source or the emitter of the device. If you're using BJT, is emitter. If you're using FET, it's source. Never put anything there. Don't use any negative feedback loop or anything, because at low frequency, your device might get destabilized, but this negative feedback loop or inductor which you put here will kill you at high frequency. This will give you a lot of stability problem at high frequency. Ideally, when you prepare your PCB, your emitter or your source should be grounded as seamlessly as possible. It should be very transparent ground. You should not have any kind of feedback, which might come in here. Okay. So in this case, as you can see, I have put a series resistor at the output, and I have a shunt RC network at the input. Now, you typically don't like to put a resistor at the input series in RF signal path, because this directly means loss. Anything loss means noise figure. So if you want to achieve good noise figure, you should not have any series resistance in the LNA input series path. Here, output is safe bet, because by the time this signal comes across this device, the signal has already been amplified by this transistor. So remember the cascade noise figure formula. The contribution or the noise figure degradation due to this resistor will get divided by the gain offered by this device. So here it will have least amount of impact. If you are doing power amplifier, you will do exactly the reverse thing. To stabilize this device, you will put this resistor at the input, because in power amplifier, this signal will be very high, and you don't want this resistor to eat away the power that you have achieved after a lot of struggle. So putting this, resistor at the input will be much better choice. So here, to achieve stability, I also had to put resistor capacitor network at the input. But here you can see I have put a much higher resistor to minimize the impact. I needed to do this in order to achieve a broadband stability on this transistor. So if I simulate, now you can see in mu and mu prime, your mu is greater than 1, which is this red curve for the entire bandwidth, and the blue, which is mu prime, is greater than 0 for the entire bandwidth. So now this device becomes unconditionally stable. Now, when you're trying to stabilize the device, pay equal attention to the gain, because it's very tempting to keep increasing resistor value to stabilize the device, but then you can't also sacrifice the S21, right? Because if S21 goes below, then you also have gain target to meet. So always keep an eye on both of these things, and also not to forget noise figure. As you can see right now, the NF minimum, which is the inherent noise figure, even if you do the best noise match to this LNA, you will be able to get 0.96 dB. So keep an eye on your target noise figure. Remember, right now there is no impedance matching network, there is no PCB loss, there is no transmission line. Basically, what you are seeing is just the inherent transistor with, you know, 2 3 components like resistor and capacitor. And you already need to be worried that you are going very close to 1.4 dB already. Okay, so be mindful of that. So take care of all these 3 things here. S11 S22 is not my concern right now, but noise figure, stability, and gain have to be balanced. So in ADS, what you can do, there is something called real-time tuning. While you are trying to balance the performance, you see this tuning fork icon in ADS, and this tuning fork icon, basically you can select the component, and now you can place this tuning bar next to your data display here, and now you can start changing the parameters and live see the impact on how things change. So this way you get a sense of where things are moving when you are changing the component values and so on and so forth. So this gives you a pretty good idea of what's going on there. Okay. All right. So one way is to do tuning. Other way in ADS is called optimization, which we will see in a short while. But you can set up and run optimization and let ADS compute the right value of these components to achieve the targets which you are looking for. Okay, so let me keep moving on quickly. So once I have stabilized the device, I should focus my attention to designing a bias network. So as one of the comment earlier said, if I don't have a nonlinear transistor model, if I don't do DC simulation, how do I decide the DC feed and the DC bias network? As you can see, it's a purely S parameter simulation. So let me activate some of these terminations so that you can check the performance. Now the goal of bias network, depending on the frequency which you are using. So this one is high frequency design. I decided to go with a transmission line based circuit. So as you can see here, this is the quarter wavelength line. So the magic of quarter wavelength line in RF microwave should be known to everyone. But in case you forgot, let me explain. So what's the purpose of this DC bias network? The purpose is my RF input will be coming at this terminal. I want entire RF input to seamlessly go to port number 2, right? I don't want any RF to come into this DC. And at this point, I'm going to feed my DC bias supply. It could be gate bias or drain bias and things like that. So I don't want RF to come and disturb this piece. So how do you achieve that? So if you apply a ground or a short here, your RF should see an open circuit at this point, right? At this junction. If it is an open circuit, the entire RF will go into forward direction. Nothing will come here. So quarter wavelength line does the impedance transformation, correct? So if you present a short circuit here, you will produce a open circuit here. Your entire RF will go away. So that's the concept of quarter wavelength line. Now, depending upon the dielectric material you are using, how do you do lambda by 4 calculation? ADS has something called line calc. If you go to tools, line calc, you can start line calculator. And here you can enter your dielectric specification. You can enter the frequency you want. You can enter the impedance you are looking at. You can enter the electrical length, like for quarter wavelength line, it is 90 degree. Now this always is a high impedance line depending upon the fabrication limitation. So sometime I have seen people use 85 ohm to 100 ohm kind of impedance, depending upon what you can etch. And so once you enter this, specification on a specific dielectric, when you say synthesize, it goes and calculates the line dimension. So here you can see it is saying for 100 ohm on this dielectric, you need 1.25 mil line, and that's the length of the line and so on. But right now the dielectric is too vague. But this is how you can do a very quick calculation of the lambda by 4 line. Here you can see effective dielectric constant, attenuation in dB per meter. You can see skin depth and so on and so forth. So pretty nice utility to have there. Okay, so at this point, if I simulate, this bias network, you can see at 2.4 gigahertz, your S11 is minus 60 dB. It's minus 59 dB. What does it mean? It means your input termination and output termination are directly connected with each other. So this shunt network is transparent. That is what it means. S11 is almost near perfect, correct? Now, when you look at S21 at 2.4 gigahertz, S21 should be minimal because this port is directly connected to that port. So basically, you only have 2 mm, 2 mm, 4 mm line in between. And at 2.4 gigahertz, that's not going to give you a huge amount of loss. That is what you are seeing in this response here. But lambda by 4 line at 2.4 gigahertz becomes lambda by 2 at 4.8, and that's why you can see it gets rejected completely, because that sees a short circuit, and that is why you can see S21 is showing you a short circuit, so you get minus 30 dB kind of isolation. So that's how you do a good design of a bias network. Okay, so let me go ahead and deactivate some of these, and then let's move on quickly. I'm a little behind time, but the good news is everything which I'm presenting is already covered in 2 tutorials, which are 1 hour each. They are available on my YouTube channel. I will shortly show you where they are, and there I have explained some of these things in little more detail so you can get exposure. So once you design the bias network, you design everything, now you need to find what kind of impedance I need to match my transistor or this network. So a very common mistake I have seen people do when they look at Z11 or Z22 or S11 and S22, they directly start looking at the device. But remember, it's not only the device, right? So your device have to be mounted on the PCB. So now you can see I have included a transmission line. I started doing, what will be the land or the footprint where my device lead will come and sold, because inherently that line becomes part of the device. Your device is not working in isolation. Remember, we had a RC network. So RC network is not going to be like this. It has to be mounted on the PCB. That means it will have a footprint. And now you can see I have modeled the footprint. And in RF microwave, it's very crucial to look at the discontinuity. Don't connect wire and build a T network, something like this. Never do that. Because if you do something like this, that's fine, but then you are missing this entire discontinuity effect, because now you have a T junction. Never do this, because then you never see a right reflection. So everything which you are doing is not going to work in real life. So start implementing and account for this discontinuity from the very beginning. Okay, wherever you have junction, use T, use cross. If you look at transmission line library in ADS, so here is your T lines microstrip. You have all these discontinuities, corner curve, corner bend, then you have step. If your width has mismatch, you should use this step component in between, so that width mismatch effect reflections are taken care of. You have these T junctions. You also have cross junction if you have, let's say, a 4-way connection and so on and so forth. So all those discontinuities have to be model from the very beginning. So don't underestimate what problems these discontinuities can create. So if you look inside my bias network design, you can also notice the use of this T junction with the variable. And again, other best practice is whenever you're dealing with such circuits in for your circuit design, instead of directly providing the number like width like 2 mm or 0.5 mm, I recommend you to use this variable. So how this variable helps: number one, even if the same, you can see W50 here, W50 there, W50 here, W50 there. If I decide to change W50, I don't need to go into these many components and change that value. If I change the value at one place, it will automatically propagate to all these components, and my circuit will always be in sync. It will never have a situation where this is point 0.2 but I forgot to update this and this is still point 0.4. That will give you a wrong reflection. You will do a wrong design, and you might realize it once you go very far in your design process. Okay, so use this variable. Account for this discontinuity is very, very crucial. So at this point we will go ahead and simulate, and then we will figure out. Okay, so here you can see in the Smith chart, I am plotting gamma optimum, which is this blue curve. I'm plotting S11. So if you go and match your transistor to this impedance offered by S11, so in this case my marker M5, so 8.7 minus J8 ohm. If you match your amplifier here, you will get conjugate match, you will get the best S11, but then may not be good noise figure. You can see the noise figure is here, right? So, and these two are different impedances. So if you match for noise figure, which is 19 plus J2, you will not have a good S11. If you match for S11, you will not have a very good noise, right? So that's the whole art of LNA. So how do you overcome that? Well, there is something called noise circle and gain circle. So here you can see I'm plotting two things. One which is noise circle, another which is gain circle. So you can see M8 marker, which is placed on this small circle inside, that is gain circle. And noise figure is M9, which is this bigger red circle here. So the ideal place, you first finalize the desired noise figure. For example, this M8, or sorry, gain or noise, either way. So this is 16 dB gain circle. So I'm trying to obtain 16 dB gain out of this amplifier. My target is 14, 2 dB extra margin. And then this is noise circle. So every circle is representing one noise figure value. Like M9 is placed at 1.1 dB noise circle. If I place it here, now you can see it's 1.2 dB noise circle. If I place here, it's 1.3. So if you want to find a compromising point, just go and look. You see, at this location, these two circles are intersecting. So if you can find this impedance point, let's say right now what I placed on M9, so M9 is offering this impedance. So if you match your amplifier to this condition, you will get a good gain and you will get a good noise figure. So that will be a good compromising point to achieve best of both worlds. Exactly same thing we do in power amplifier, but we do it with respect to the power added efficiency and output power. That's the compromise we need to do in the power amplifier. In LNA is noise and gain. All right, so once I know the impedance I have to match for, of course you can proceed and start doing impedance matching design in areas, and you have plenty of nice tool to do impedance matching design. And once I do that, here is my total circuit. So if I push in here, you can see this is my input impedance matching network along with my coupling capacitor, and this is the matching stub. This is the matching line, which I'm, so this T junction is what my input impedance matching network. Rest, you can see the use of this discontinuity, because SMT components you will buy which has 0805 or 1206 size. So this footprint I have modeled using that dimension, and then I use this step because this will be wide line, this might be smaller line, or vice versa. This might be thin line, this might be thick line, and so on. Okay. So that's your entire input side of the amplifier. That's your entire output side of the amplifier. And once you assemble all these pieces, the performance will vary a little bit. And that's why I am using optimization to decide on optimization goal. I optimized my design, and if I simulate it, this is my optimized overall LNA. So you can see it's a pretty flat noise figure with 1.2 dB, and my target was below 1.4 dB, so this seems to be okay. Stability factor is, meeting all the criteria. The gain is meeting all the criteria. It should be more than 14 dB. You can see in the entire band it's more than 14 dB, so it's pretty good. S11 and S22 is meeting the requirement. It should be below minus 15 dB. So I'm able to optimize my overall circuit to meet my specification. So next step, of course, is to go and do layout design of this transistor, and then we can proceed to do electromagnetic simulation. So here you can see we have the input matching network layout. Again, as I said, it's not highly optimized. I have plenty of opportunity to bend this line and make it something like, for example, something like this. To reduce the size of this line, I can reduce the size of this line, I can reduce the size of this line. So overall, you can make it more compact, LNA, size. So that's input matching. And then we do output matching. That's the network of output matching. Again, there is a scope to squeeze the size and so on. And then what we do individual EM simulation. And then here you can see this is EM circuit core simulation, because so far we have been using transmission line model, which is okay, but transmission line models are analytical equation based. What if there is a parasitic coupling between these two lines? I'm a new RF designer. I forgot to follow the thumb rule of not letting two lines come closer than a specific number. Then you will have a parasitic coupling and so on. So now, instead of that, I'm doing an EM simulation, and then I'm doing this virtual PCB assembly, so that I take care of every coupling which is happening on this side. Similarly, this is output matching network. And then if there is an imperfection, I can optimize my design again, right? So you can see slight degradation in noise figure, because now electromagnetic simulation, radiation loss, coupling, everything is accounted for. So I'm still below my target, but I'm getting very close to the target, right? That's why the transistor model, remember, my target was 1.4. I said you should pick noise figure minimum to less than or equal to 0.7. And my transistor had close to 0.6. All right. So it was already touch and go. And that's why you can see you are almost there. So lower the noise figure minimum you can choose for the device, more headroom you will have to guarantee to meet the specification which you are looking for, unless you mess up your design in a very bad manner. So I would prefer still have like 0.3, 0.4 dB inherent device noise figure, and that will give me very high headroom. So in the previous section, we did input side EM, output side EM separately. But then we can do a final layout, because that's how my PCB will look like. And I will do a full electromagnetic simulation of this entire layout. Reason I didn't do it from the very beginning, because I just want to make sure that you have the right confidence in the result before I go and do this complete layout. Because when you do a big layout EM simulation, it takes some time. So I divided the problem into left half, right half, attained the confidence when everything is working okay. Then I went ahead and created this entire layout. Another good tip, if you're doing such design, you see, consider the number of via holes I have, because this is where I will mount my design. And remember, I mentioned the source or the emitter terminal of your transistor should be almost fused with the ground. That is why you can see I have so many via holes where the body of the transistor will sit, and these via holes will provide, very nice ground to the body. And this is the place where my terminal, my emitter or my source will come. You can see I have a good amount of vias there to fuse the emitter or the source directly to the ground. So you should have no conjuicy in doing more via holes here. Put as many via holes as you can closer to the device, so that you get the most least resistive path to ground. Okay, don't be very, like I only have one via or two via and I will be okay. If you do this wrong, the whole amplifier can become oscillator very quickly. So have lot of via holes right there. Okay, so I'm cutting very close to my final time, but let me quickly show you here. So that's the final layout assembly. This is like a virtual PCB assembly. You can see your PCB, your components mounted on that PCB, and you run the simulation. Never fabricate your circuit without doing a full circuit EM co-simulation. And if you get the good results at this point, you can be very confident that you will have a proper working circuit when you fabricate. So we are meeting all the specifications as needed. Now finally, somebody asked, how do I simulate P1dB? Well, in ADS, that's what we do. We have something called harmonic balance analysis, and that allows you to simulate nonlinear performance. So now I go ahead and run. You can see the output power. You can see second harmonic, third harmonic, fourth and fifth harmonic. You can see it's a class A amplifier. You can see full 360-degree conduction in the output. So that's the static harmonic balance. You also can do power sweep, input versus output power sweep. And here you can see input versus output power. You can see gain versus input power, and that's how you find P1 dB point. You can find where your gain is getting compressed by 1 dB, and that's your input P1 dB point. And at P in equal to 0, that's your output P1 dB point. So that, and you can also see how harmonics are changing with input power, and you can see the slope of harmonics are different. This is what we read in textbook, right? Third harmonic will have 3 times slope, fourth harmonic will have 4 times slope, 5 times slope, and so on and so forth. That's how you do it. And then once you are ready to fabricate this PCB with the final layout, whatever you prepared, you go to File, Export. You can export DXF, GDS, Gerber, ODB++, and then you can give it to your PCB fabrication house and you can use it. Okay, so at this point, I would like to stop here. Let me quickly take some question if we have time. I know it's bang on time, but do we have 5 more minutes to quickly take some question?
Yes, sure, sir.
Okay, so let me see, where do I have. In some cases, BPF is used as a first stage of receiver. Yes, absolutely. Sometimes you will have BPF right at the input, and that will impact your noise figure performance of the overall noise figure of the receiver, and you can't do anything about it. You need to just take it into account while doing a proper system budget calculations and so on. Keeping a series resistor in the output will not reduce gain. Yes, it will reduce up to a certain point, and that's what I mentioned, that you need to balance the stability factor and gain. You can't compromise on the stability even if you go down in gain by 1 or 2 dB, because stability is the most important thing. So, but you need to maintain a balance there. Can you show the layout? I already showed
.cs.
you how to check. Sorry, somebody is speaking. Can you mute yourself if you're not speaking here? Okay. How to check P1 dB? I just showed you using harmonic balance. Can you show the way noise figure is set up? Oh, okay. My apologies. I missed out on that. That's pretty simple. Actually, so here under S parameter, you go to parameter and just switch on under noise, you switch on the calculate noise. And once you do that, all noise calculations are done. And when you look at output, the actual noise figure you need to look for is NF2, which is noise figure at port 2. You also get NF minimum, which is your minimum noise figure. Okay, so let me see what else you have. Can you shed some light on what functionalities are different in doing POSIM and RF probe? That's a little long question, so I will let local Keysight team answer you, Madhvesh, on that. Please tell me how to insert vias. That's pretty simple. And again, somebody from India Keysight team should be able to discuss with you, Parul, on that.
This one.
Will you provide transistor S2P file so that I can unzip and start designing? When I share this workspace, you will have this nonlinear library also included in that, so that you can directly start designing using this device.
So
Okay,
there is small straight line, okay?
I don't know where is this noise coming from. Okay. Let's look at chat. Is there a convention of placing VRs maybe in terms of lambda G? If you are talking about VRs near the device, no, there is no rule. Just go ahead and place as many as you can. That's simple as that, because the idea is that the source or the emitter terminal of your transistor should be almost fused to the ground. So more VRs you can put it, better it is, because that is almost like shorting those terminals. So don't worry about lambda G and all that. So just place as many as you can. While performing simulation, sometimes we get temp error, which shows we need to set temp 16.85. Why this error comes? Okay, that error comes. That's not error. That's actually a warning that comes because, as per IEEE definition, the noise is calculated at 290 Kelvin. And by default, the temperature in areas is 25 degrees. That's the ambient. So if you want to avoid that warning, then you should place an options block, like I might have done it here easily. Options block and set this temperature to 16.85 so that you are adhering to IEEE definition. Okay. What I say, placing vias all over the PCB is good approach in case of wideband impedance matching. I'm assuming you are referring to via holes, which you see here. Yeah, it's a good approach. It helps you in EMC, any radiation coming out from some other circuit and trying to affect your circuit. These via holes will provide a path to ground so that your functionality or your amplifier will not get affected. And by the way, don't get fooled by this approach. This is not a CPW design in any manner. I have placed enough consideration to keep this separation more than required CPW. So it's a pure microstrip line. This is something what we call as copper pouring in PCB. We just pour the copper, we put the via holes to protect our circuit in the harsh environment, to protect it in condition of EMC. What was the last simulation? Momentum FEM. I use momentum, but you can use momentum or FEM, absolutely no problem. Did we also look for output IP3? Well, due to lack of time, I didn't show you, but here is a two-tone setup. Here we are feeding two tones with 1 megahertz apart. And once you do that, you can look at output IP3, which is 28.5 dB. Our requirement was greater than 20 dB. So, okay, how do I add boundary to the overall layout design as you have added? I'm not pretty sure. I didn't add any boundary. It's just the copper boundary. Shall we try to have 3D shapes of discrete elements? It's not required. 3D shapes of discrete element is just visualization if you want to, but frankly speaking, it's not required. 3D simulation doesn't mean 3D SMT model. 3D simulation only simulates your PCB and the copper trace and everything. Anyway, no EM simulator simulates your SMT device. Want to design such as portable jammer? Not pretty sure about that question. I guess you might consider talking to local Keysight team. Can you tell us how inductor in source affect gain at high frequency? I would never recommend to have inductor in source degeneration. If you're doing traditional RF microwave design, if you're doing RFIC, might be okay, but definitely not in PCB. It will give you headaches in high frequency. It will cause serious oscillations at high frequency. What resistors we use? Are they sort of RF? Every SMT resistor is a RF resistor. There is no special meaning. We are not using leaded, resistor. They are all SMT. They are by default RF resistor. There is nothing special thing which is called RF resistor. Can a wide range LNA be designed from 10 kilohertz to 40 gigahertz? No, not with PCB for sure. If you want to do that kind of LNA, I would say look at MMIC. That's your only choice. Or look for some LNAs which you can get off the shelf from companies like Corvo, Maycom, Skyworks, and so on. Could you provide all these files so that we can practice? Yes, the ADS workspace will be shared with you along with the slides which I have presented today. Which design technique will be effective, like cascade, cascode? I mean, that's a difficult question to answer. That depends on what implementation you are doing, whether it is MMIC, RFIC, and so on and so forth. So in MMIC or RF board, you don't use cascode for sure, but you can of course use multi-stage LNA design. But if you're doing RFIC, yeah, maybe cascode might be used. When we set up the layout using transmission line model, circuit model, we just create the lines by entering dimension manually. There are many options, Indula. There are many ways to do ADS layout design. Again, as I said, if you go to my, let me bring this up. So if you go to my YouTube channel there, and if you look at various playlists I have, one of the playlists is RF design tutorials. So here, if you go, you will find plenty of design tutorials like impedance matching, fundamental, broadband, impedance matching, distributed. The same LNA topic that I covered is also there in two-part lecture. You have multi-technology, load pull, power amplifier design, and so on and so forth. So and here are two tutorials of RF layout designs in ADS, part 1, part 2. You have some power divider, CPW. How do you account for these SMA connectors? How can you simulate your circuit within a housing, within a box? Because a lot of time you might find you do a very good PCB design, but you put it in a box, close the cover, and things became very different. So how do you tackle all that is very nicely covered in this 3-part tutorial. Okay, and then there is RF switch design, which is again a PCB switch, and so on. Can we use any other tool other than ADS for design LNA? Yeah, there are other tools available on the market. You can definitely use whatever tool of your choice. But if you ask me, I would say ADS. That's one of the best tool you have available. But as a user, you do have choice. Can you share any document application notes, via strategies? I don't have any application notes or design guides and all that, but whatever I have are covered in this tutorials. This is actual RF circuit design. If you have never used ADS, then look for a playlist here called Learn ADS in 5 minutes. That will teach you everything you need to know about ADS. So it has like 60 plus videos. Each video is like 5 to 6 minutes, most of them. So it's a very short video, gives you very precise knowledge on every topic which you have to have in ADS. So that's actually a very exhaustive list. So go ahead and watch those to learn ADS. We need similar session for PA design. Well, for PA design, as I said, you already have a 3-part tutorial on YouTube. You can go ahead and refer, but in case local team sets up any session in future, we will take a look at PA design. In terms of frequency band of operation, how do you differentiate between RFIC and MMIC? It's a difficult question to ask, but usually RFICs you will find decent performance till sub 6 gigahertz. MMICs can go very, very high frequency. MMIC will definitely have better noise performance than RFIC because silicon is a noisy substrate. So it's not very suitable for a good LNA design. But again, it depends on the objective. If you are doing SOC kind of design, then of course you will work with silicon. MMIC will be much better LNA because gallium arsenide is much better substrate, which is a good noise performance. What can be better approach to tackle deviation? We may get into practical results. Yeah, there are many considerations. Again, Arijit, there are a lot of these things covered in my RF design tutorials on how to make an idealistic design to practical design. There are lots of tips and tricks offered if you watch LNA video, PA design video, and everything. Yep. So there are some things. So you need to make sure you model everything. But take it from me, if you model everything properly in simulation tool, every design you do should be a first pass success. As I said, my maximum deviation you can expect is plus minus 5%, not more than that. And usually, most of the time, you will end up getting into plus minus 1 or 2% zone between simulation and measurement. Yeah. Okay, Surma says, I want to say thank you. I've been learning ADS from your videos. That's excellent. Thanks for the feedback. That's why videos are meant for. So keep watching and keep learning. I am beginner to LNA design. Kindly suggest where to start. And that's why precisely you were in this session, Ashwin, to learn about LNA design. And again, as I said, if you want to learn more, feel free to go to my YouTube channel, look at RF design tutorial playlist. You can watch everything which you need to know how to start with, RF circuit design, including LNA design. And there are a lot of other references available online. You can find, multiple application notes, videos from other people. So there is no shortage of knowledge these days. A lot of things are available. All right. So with that, I think we have crossed 15 minutes to our allocated time. So I need to stop here. I know you may have a lot of other questions, but feel free to get in touch with our Keysight India team. We have very experienced people based in Bangalore, and they travel all over India. So you will have, good support experience. They will be able to help you wherever and whenever you need. With that, thanks a lot for your attention. Thanks a lot for your active participation. If anything I can do to help you, feel free to let the local team know. They can reach out to me. And again, at the end, keep subscribing to my YouTube channel. Keep watching new videos. And never forget to put in your valuable comments after you watch the video. Thanks, everyone. Thanks a lot for your time.